Okay, so I've been ever so casually stalling, but today is the day that our assignment is due. So you've got 2 minutes to hand in your assignment. Otherwise, it will be considered one of our 2 free late assignments for the semester. If you've already handed it in, that's awesome. I really appreciate it. We can now go to our notes because we are going to continue doing our notes. Now, if you're not going to get the assignment done in like the next minute, then there's no point rushing to get it done. You might as well just stick around at lunch and get it done at lunch. There's no point rushing to get it done right now if you're not going to get it done in the next 30 seconds. Okay, so let's go ahead and let's continue our conversation on pulleys here. So here I have a pulley. I literally have a pulley system represented in front of you right now. And so what's going on here? Well, there's a pulley that's hanging from a string attached to, well, the speaker, but whatever. I don't know how sound that is, but it is what it is. So this pulley wheel, it is holding up a wire or a rope or a cable or a chain or a something, and that rope, string, whatever, right now I've got 2 masses attached to them. And I'm curious, how does a pulley work? It's a battle between 2 forces. What are the 2 forces at play here in this pulley system? What are the 2 forces battling each other? Force of tension and force of gravity. Good. So for this weight that's on the left-hand side here, there's a force of tension and there's a force of gravity. So there's a battle there. Now you tell me which force is greater, the force of tension or the force of gravity? Yeah, on the right-hand side. Or is it a trick question? It's a trick question. Why? Why is it a trick question? Okay, Brennan, what was that? Yeah, so this thing is not, it's not that it's not moving. And I want to be really clear. I'm going to be really semantic with you right now. Can something be in motion and have its forces be balanced on it? Can something be moving but still have balanced forces? Yes. That's exactly right. Yeah, that's a great example, Brennan. So a plane that's flying through the air is applying a force in the forward direction, but it's also feeling air resistance in the reverse direction. And as long as you apply the same force as air resistance, the 2 forces cancel each other out, and you don't speed up, you don't slow down. You stay going the same speed. But what we can say is that this weight here, this mass, that's on the right-hand side, it's at rest. And because it's at rest, it's clearly not accelerating. So what can you say about the 2 forces acting on it? They're equal. Equal and opposite, they're balanced, right? Same thing on the right-hand side. So, okay, so what could I do to take this system out of equilibrium? What could I do to cause an imbalance in the system? Chris? Ooh, I could add a weight, right? Now, do you want me, I don't even know where did I put it? There's a big pile of them over there, but man, damn you, Walton. Okay. Do you want me to add a big weight or a small weight? Ooh, let's add a small weight. It was right here. It was hidden in plain sight. So we're going to add a small weight. I'm going to add a small weight to this right-hand weight. And because I'm adding extra mass to the right-hand weight, which force in particular is increased? The force of gravity on the right-hand side. So not only is this a tug-of-war between tension and the force of gravity, what else is this a tug-of-war over? It's a tug-of-war between the force of gravity and the force of gravity. Would you agree? So the force of gravity on one side versus the force of gravity on the other side. So if I add a mass here, right, then I increase the force of gravity on the right-hand side. What do you expect to happen when I let it go? The mass on the right-hand side will accelerate. In which direction will it accelerate? It will accelerate down. And the mass on the left-hand side will accelerate up. 3, 2, 1. Ah, perfect. Okay, so absolutely that's the case. Now, what if I, instead of attaching a small mass, what if I attach a really big mass? What will I do to the system? What kind of a change? How will it be different from the small mass? It will be a greater rate of acceleration. Okay, ready? 3, 2, 1. Ah! That was way faster, right? So this is the idea here, is that it's often easier for us to think about a pulley system like this as a tug of war between two forces. The force of gravity here and the force of gravity there. And that's often why we try and express pulley systems as a system, right? So how do we answer pulley-style questions? I'm going to take this and shove it in the back. See you later. See you next semester. Oh. Here's a different type of example. October 21st. Calculate the acceleration of the mass on the table if the tabletop is frictionless. So we're going to draw a diagram. We're going to have like a tabletop. On the tabletop is a mass. We're going to call that mass A. Now it's connected to another mass through a pulley. So at the end here, we've attached a pulley. And there's a rope or a string that goes all the way from A and wraps around to B. And it tells us that the mass of A is 10 kilograms. The mass of B is 4 kilograms. Should be 10.0 kilograms. And we're going to remind ourselves why sometimes treating a pulley system as a system, and sometimes we don't want to treat it as a system. What are the advantages and the disadvantages of doing that? Okay, so let's take a look at each individual component, and let's draw a free body diagram, and let's see if we can analyze each individual component and come up with an answer. So let's do a free body diagram for A. a free body diagram. Just have like a dot. What are all the forces that are acting on A? Ryden? The force of gravity, absolutely, right? It's close to the surface of the Earth, so absolutely there's going to be a force of gravity. It's sitting on a surface, isn't it? So is that surface going to apply a normal force to it? Yes, it will. Are there any other forces acting on it? Josh? There is, yeah. So we're going to say, I would rather us call this, instead of the force applied, I would rather call this the force of tension, because it's a rope, string, chain, something like that. But you're totally right. Could you call it an applied force? Totally you could, right? Something is applying a force on this thing, right? Totally. Are there any resistive forces that are preventing the motion of this object? No, there are no resistive forces because it's a frictionless tabletop. So what we're saying is, I don't know, maybe somebody froze this thing and there's a surface of ice on there and it's just gliding gently on the surface of ice. Or maybe there's tiny little ball bearings on the surface, right? And that box has been resting on the ball bearings and it's just going to float across the ball bearings. Does that make sense? So whatever, there's lots of ways we can kind of approximate a frictionless surface, but we do this to simplify systems. Let's do the free body diagram of B. What are all the forces acting on B? Okay, so there's two forces. There's the force of gravity, and there's the force of tension. It's not sitting on a surface. There's no normal force. Nobody's applying a force other than the tension in the rope, string, chain, whatever, wire. Okay, what do we want? Sorry, what's the question asking us about? We want acceleration. Now, when it says the acceleration of the block on the table, the mass on the table, do I have to solve for the acceleration of mass A? No. Why? Because the accelerations, they're connected by a string, and the string, you can't stretch it, right? Or at least that's an assumption that we're making. So if one of them accelerates, the other one also has to accelerate at the exact same rate. It does not matter which acceleration you solve for, they are the same. Okay, so in order to solve for the acceleration of A, first of all, do we care about Fg and Fn right now? No, why? Yeah, because what's the net force in the y direction for A? 0. Is it accelerating up or down? Is this thing magically rising off the tabletop? No. Okay, so the net force in the y direction is 0 as far as we're concerned here. So if we want to find the acceleration of A, what do we need to know? The force of tension, right? Oh, okay. Do we know force of tension? Shoot. So can we solve for free body diagram A? Not right now. No. Okay. Well, what about B? If we find the acceleration of B, then that's the same acceleration as A. So, okay. Do we know the force of gravity on B? Yeah, you do. You can calculate that really easily. Do you know the force of tension? Man, shucksy doodles, huh? So we need to know the force of tension in order to solve for the acceleration of the system. But we don't know the force of tension. So how are we going to simplify the situation? How are we going to try and get rid of the force of tension? What could we do? How could we mentally do this? Ryden? So let's take a look at the system as a whole. But what do we have to do in order to analyze the system? What do we have to do to these masses? Yeah, we got to straighten it out. So we got to take any masses that are hanging down. We got to mentally bring them up. So we're going to take this mass and we're going to swing it that way. So when we reframe our perspective as a system, This is basically like block A and block B are in a tug of war with each other. All we care about right now are the forces that are opposing the tension, any forces that are like an opposition of tension. So free body diagram A, does it have any forces that are opposing tension? No. So do we care about Fg or Fn? Nope, don't care about it. What about free body diagram B? Do we care about any forces, Ryan? Ooh, so if tension's going that way, then what direction is force of gravity acting on B? It's acting on it this way. FGB, force of gravity acting on B. So remember, if we treat this as a system, all of a sudden, tension, is it an external force now? No, it's an internal force, and you don't care about internal forces, right? That has absolutely no effect on the system as a whole. So we get to ignore the force of tension because it's an internal force. Okay, so actually, this is going to be awesome. What are all the forces that are acting on our system that we care about? Force of gravity on B. That's it. So let's write an F net equation for this thing. F net equals, is force of gravity B, is that a positive or a negative force? Do you want it to be a positive or a negative force? So for B, do you want down to be negative or positive? Negative. Sure, negative. So that means up is positive. Well, what does that mean for A? Is to the left, is that positive or negative? Take a look. If this block goes down, that's negative. And it would pull A to the right, so that must be negative by definition. If we're saying this way is down, or is negative, then negative is down for B, but to the right is negative for A, and that has to be positive. If that's what we're saying, if that's what we're describing. So for B, down is negative, up is positive. For A, right is negative, left is positive. I don't care, but that's the system that we're using right now. Okay, so F net, what's the only force on it? FGB. Already I've made a mistake. What have I made a mistake of? Yeah, it's, well, so that, but also what has to be in front of this? A negative. If we're going to do the style that I'm teaching you to do, right? It's a negative force. So now let's break it down a little bit more. So F net is just M times A, but which M? Yeah, it's F net is always the mass of the entire, whatever you're looking at, whatever your free body diagram is talking about. Here, our free body diagram is looking at the system, so it's the mass of the system times acceleration of the system. And then that equals negative mg, but m of who? Whom? Is it the mass of the system again? It's just the mass of B. When we look at this thing, it's just the mass of B that is included in our force of gravity of B. So it's just mass of B times acceleration due to gravity. This is a simpler system than the one that we talked about on Friday, but it actually feels more complex because there's kind of different things going on. Okay, so we want acceleration. That should be no problem. The acceleration is negative mb times g over m of the system. Okay, that's easy. Mass of B is 4 kilograms. Acceleration due to gravity is 9.81 meters per second squared. What's the mass of the whole system? 14 kilograms. Negative 2.80285 meters per second squared. Negative 2.80 meters per second squared. So instead of writing negative, because negative means weird things in a pulley system, right? Does negative mean the same thing for every block? No, so you have to be more explicit about this in a pulley system. It's not good enough to just say negative is down, because negative doesn't mean down for every single block, right? So what direction is this block going? If you said it, I didn't hear it. Down, up, left, right? Lila? Right. Which block are we talking about? The one on the table. Remember? The question says, what's the acceleration of the block on the table? Yes, block B is going down. I totally agree, block B is going down. But the acceleration of the blocks is the acceleration of the system. Everything is accelerating at the same rate. So block B is accelerating at 2.8 meters per second squared down, but block A is accelerating 2.8 meters per second to the right, because that's our negative. I want to be really clear. Once you solve for acceleration, now, like, this is the only point in time where you can actually go in and solve for tension. So if I ask you what is the force of tension between the two masses, you have to get acceleration first, and now you can get the tension. So what do you think the next question is? What is the tension in the wire? Rope or string? Yeah, Chris.
Is this only true when frictionless?
How would this have changed? That's a great question. How would this system or situation have changed if it wasn't a frictionless system? Like, what's the only thing that would have changed, Josh? What do you think? Do I have to minus the F net from the what? Yeah, so if I was asking for force of friction or something like that, but like what I just want to ask about is, if this table wasn't frictionless, what would change in our free body diagrams? What's the only thing that would change in our free body diagrams? Natalie? For a free body diagram of A, there'd be a force of friction. And then, so because that's opposing force of tension, how would the system have changed? There would have been a force of friction, right? So we would have had to have added force of friction in here. So, Chris, I would have had to tell you what the force of friction was between block A and the table. I would have had to tell you the force of friction between block A and the table is 30 newtons, or whatever, right? Yeah, but I would have had to state that for you. Yeah. Yep, that's a great question. But now we can look at what's the tension in the rope, okay? So now we do want to figure out what the tension in the rope is. Can we look at the system as a whole to figure out what the tension in the rope is? No, because tension's an internal force. So what do we have to do? We have to go back to either one of these drawings. Which drawing do you want to talk about? B? Sure, that's totally fine. Which one's simpler to talk about? A is. Because A is accelerating in a horizontal direction, right? It's going this way. And how many forces do you have in a horizontal direction here? Just one. That's all. So it's actually easier to talk about A. But somebody said B first, so that's what we're going to do. So let's take a look at free body diagram B again. Nope. It's not that bad. It's going to be totally fine. Okay, so what can you do with a free body diagram? What's the only thing you can really do with free body diagram? Yeah, you can write, yeah, there you go. You can look at the pretty picture. So F net equals, now what we can do is we can reframe our positives and negatives if we want to. We can decide, do we want to change our positives and negatives? So you tell me, do we still want down to be negative? Yeah. Sure, whatever. That's fine. Down is negative, up is positive. I got no problem with that. So we go ft minus fg. Again, you could go plus fg, but then your acceleration due to gravity would have to be negative. Okay, let's break all of this stuff down. F net. Can we break F net down into something else? Mass times acceleration. Mass of what? Yeah, so this is just block B. You look at a free body diagram, the F net, the mass inside the F net is whatever we're talking about in a free body diagram. So this is just block B. It's no longer the mass of the system because we didn't draw a free body diagram for the system. That's equal to Ft minus, and then Fg is just mg. Well, mass of who? Whom? This Fg, it's block B. Good. Okay. Well, this is really easy. You want Ft. So rearrange, add mb times g, right? Add that last term. Move it over to the other side. It's mass times acceleration plus mass times acceleration due to gravity. And it's mb. Let's put all this information. Do you know what the mass of block B is? 4 kilograms. Do you know what the acceleration of block B is? Good. It's negative 2.80. Use your rounded or unrounded value? Unrounded. Good. We're used to that by now. 285. Plus 4 kilograms again. And then acceleration due to gravity. I know people want to write negative for acceleration due to gravity, but we already took the negative into account up here. The negative is there already. So you just go 9.81. That negative is going to make a big impact. Did you get positive 28.028? Blah, 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 blah. Okay, so the force of tension is equal to 28.0 newtons. And remember, when I say force of tension, the force of tension changes through the rope as the direction of the rope turns, right? Then the direction of force of tension turns as well. So you don't have to tell me that the force of tension is up, okay? Because the force of tension is the same throughout the rope everywhere in the rope. So you can just say 28 newtons, and that's fine. Are we okay with that? Are we cool with that? So if you want to identify, if you want to be able to calculate the force of tension in a pulley system, you have to get acceleration first, and then you have to do some other stuff. Hey, holy cow, how could I be a jerk with this? Holy cow. We're not going to actually answer the question, right? I could ask for velocity after a certain amount of time. Totally.
Why is there two of them? No, please don't. This is like my version of a horror movie. This is cruelty. This should be considered child abuse.
The more you say that this is painful for you, the more you feed me. The more powerful I get, and the more it's going to take for you to destroy me. Okay, so let's let's think about this for a second. Let's think about this for a second. Kate, so what are the forces acting on A? Yes, good. Kate, so acting on A is force of gravity. Acting on A is force of tension. Okay. Acting on B, what's acting on B? Force of gravity, force normal. Do you care about force of gravity and force normal? No, you don't. Okay? Now, I want to be really clear. These two ropes, they can have the same tension. Okay? They can be under the same tension. Okay? They can be under different tensions. Okay, so there's also a force of tension here, and then there's a force of gravity here, and then there's a force of tension here. Okay? But it's not that big of a deal. It's not that big of a deal because what can you do to make the force of tensions go away? You can make it into a system. So you can treat this as a system. And yeah, your force of tension in this rope, your force of tension in that rope, they can be two different tensions. That's totally fine, FT1, FT2. But look, they're all within our system, so the force of tension goes away. We don't care about the force of tension in those things anymore. So what we can do is we can swing this up. We can swing that up. We can go block A, rope, block B, rope, block C. And we can treat the whole thing as a system. What's the only thing pulling this thing to the right? Force of gravity on block C. What's the only thing pulling this system to the left? Force of gravity for A. Now, this is if block B was frictionless, right? But if block B was not frictionless, then there would be an extra force, either resisting in that direction or resisting in that direction. But it's not that big of a deal. I think it'll make sense to a lot of people if and when you show up to a question like this. But yeah, I want to be clear. Okay, FT1, FT2, but they're internal forces, and so they are canceled out when we look at the system as a whole. Is that okay? Yeah, Chris.
Does that only work? Like, that's not in real life. The rope, is the rope gonna act like that for any type of rope?
Yeah.
Any?
Yeah.
Even an
So,
elastic rope, even.
oh no, not an elastic rope.
Okay, just like a solid.
Yeah, but an elastic rope, sooner or later, is going to find an equilibrium position, right? So it's going to stretch, but then when it's done stretching, it's found its equilibrium position, then you can treat it like a solid rope will. Is that okay? So but here, we assume all ropes, wires, cables, strings, chains, we assume them to be massless and frictionless so that gravity doesn't act on them because they're massless. They're frictionless, so we don't have to take into account the friction of the pulley wheel or the string between the pulley. And we also assume that they are not stretchable to make all the math easy like what we're talking about right now. Yeah, if you were an engineer, then you would have to care about that. You would have to sweat the small stuff, right? Yeah, Alfred.
So why don't we care what the forces be?
The forces on B, because which directions can B go in this case? Can B go up, straight up? No. Can it go straight down? No. So what do you know about FG and FN for B? They're equal and opposite. Its net force in the y direction is 0. So all we care about is FT2 and FT1. That's all we care about.
So like you never really care about any. So you don't care about the one that would be on the surface because it won't go up, it won't go down.
Yeah, this thing can only move left and right. So you care all you care about are the horizontal forces for now. Lila, question? No. Okay. 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 So what I would like you to do, you got a lot of time. Holy cow, I forgot to hand these out a long time ago. Here are the review booklets. Do you remember me saying this like a week ago that I had them and they're available? Holy cow. So I'm actually going to hand those out. But then there's pulley practice questions, okay? So I just want you to try the pulley practice questions. I'll put the answer key to the pulley practice questions out on the bench top. I don't know, I think that's enough.